Right, welcome to the Folkestone Academy live stream for the C1 exam tomorrow. We're going to be going through all the sections of C1 we can fit into an hour and a half. Hopefully you're with us live, and if you have any questions, the email address is still there. It's contactscience@folkestoneacademy.com. Questions are great. They really add to the interactivity of this. They allow us to really respond to your questions, what you want to know. As I said last time, if you have a short question, a quick question, then it might be responded to just over email. If you have a slightly longer question, something that you want more of an in-depth answer to, it might come through to me live, and I'll be able to answer it and give you exactly what is happening. Bit of background noise there while we sort out a few technical issues in our tech support area, but hopefully we're back and you're with us. This is all about making sure you have a positive exam. I'm going to give you some tips along the way and how to answer some of the questions and some of the bits you've really got to think about, and some of the little areas, units, things like that, answering exam questions, exam technique, what you're looking for. And hopefully it'll be beneficial. And we've had good feedback on the first one. Oh, forgot to say almost that the exam is tomorrow morning. So I myself will be in early, and some of the other team probably be around to go for any bits. So if you wanted to get in early, sometime from officially 8 o'clock, we'll probably be in a bit earlier in 103. Although maybe we might be in 010 tomorrow morning. I'll just confirm that towards the end. Yeah, we'll be able to give you some last minute tips and tricks just before the exam actually starts. But without any further ado, what we'll do is I'll start my timer here to make sure we're on track, make sure we cover things in a timely fashion, because in the chemistry syllabus there is quite a lot to cover, quite a lot to get through, so I want to make sure we have enough time to get it all done. In terms of what we're looking at, okay, just noticed the board's on freeze, there we go. Starting us off with the very basics. Okay, chemistry relies on the fundamentals, and the fundamentals of chemistry are atoms. They're the building blocks of all things. We need to remember a bit about them, like the structure of an atom, how that model was developed, and the subatomic particles and what's made up of them. I forgot to say actually that you can download the notes for the PowerPoint for the presentation. There should be a link with the video, so you should be able to get it there. But also, if you go to the Folkestone Academy revision website, you can get it linked to it there as well. So if you can't see this on the board, because I know sometimes that's some of the issues surrounding being able to see exactly what's written here, I'll talk about it, and often you'll see me standing in the way. But if you've downloaded these notes either before or after, you'll be able to get the information that way. So, atoms then. The structure of the atom looks a bit like this. We should be familiar with it already. You've got a nucleus in the centre, and inside the nucleus you find protons and neutrons. The protons are easy to remember because they have a positive charge, positive protons. That's the way to remember that. That follows nice and easy. So protons are positive, and they're found in the nucleus of the atom. Also with them, you've got neutrons. Now neutrons is a little bit more tricky. They are neutral, so they have no charge. Their charge is 0. They're also found in the nucleus, and they have a mass of 1. Protons also have a mass of 1. That's the mass that they're given. There's not units for that, it's atomic units for protons and neutrons. They're tiny particles, you can't weigh them in grams, so they just have a mass of 1. Neutrons have a mass of 1. Electrons, they're found in shells or energy levels that whiz around the outside of atoms. So they actually move around the outside, they're spinning around, occupying energy levels or orbitals or shells. Lots of different names for them. You can use any in the exam. Shells is quite a good one to remember. Electrons have a mass of almost 0. You can say 1 over 1,800. You could be more accurate than that, but for the purposes of the GCSE exam, you could say their mass is almost 0. You can't say, you're not allowed to say their mass is 0, because that's incorrect, and unfortunately you'll be scored down. Often the mark schemes will say do not accept 0. You have to say almost 0 or 1 over 1,800 if you want to put a number on it. The electrons are the ones with a charge of -1. They have a -1 charge, so they are negative. There's not a clever way to really remember that. You just have to remember the protons as positive and you have to remember the neutrons as neutral and the electrons are the negative subatomic particles. And as I say, they're found in shells around the outside. There is a way these electrons are organised, and we'll come to that, exactly how the electrons are organised, but for now, that's the model we need to know, and hopefully that's not unfamiliar to anyone. If it is at this point, then there's a lot we're going to have to pay attention to during this video. Now, you probably can't see all the information on this, but you need to know a bit about the development of the model of the atom, how it's changed over time. It can go right back to the ancient Greeks. Democritus came up with the idea of an atom. They could speak about him in the exam. He coined the phrase atom. It means something that's non-divisible, unable to be cut up into any smaller pieces. The sort of example they talk about, although I doubt this will be in the exam, but I quite like it, is the fact that he took a piece of cheese, he cut it in half, he had a smaller piece of cheese which he cut in half again and again and again, until he got to a piece of cheese that was the size of a grain of sand, and he said, I couldn't cut it any further. But he thought maybe if I had a fine enough blade, I could cut it up, and I could cut it up again. But eventually I would reach a point where I could not cut it up anymore. I would be at the smallest particle of cheese that I could have. And he called that an atom, or atomos, which means non-divisible, can't be broken up. It wasn't until a lot later when the idea was taken a bit further by Dalton, John Dalton, who came up with a solid sphere model. So he said an atom was just a big ball. He didn't know anything about the subatomic particles, but he realised that things were made up of atoms, and he just likened it to a billiard ball, just a solid ball, a solid mass of matter, really. It wasn't until about 100 years later, again, when a person called J.J. Thomson came up with the plum pudding model. That is one they can talk about. It came from the fact it was like a round ball of positive charge, which was the pudding, with dotted around electrons, which were negatively charged within it. And they were like the plums in the plum pudding. A plum pudding is probably not something you're familiar with, but it would be like a raisin or a currant scone or something like that, with the dots of raisins within it. So he came up with that model, the plum pudding model. It will be called that if it's referred to. A solid ball of positive charge with negative particles dotted all the way through it. Again, it started to speed up around this time, and a few years later, someone called Rutherford actually decided that the atom was a bit different to that. He did an experiment called the gold scattering experiment, where he fired like particles at a thin layer of gold, and he saw that some of those particles passed through the gold and some of them were deflected. The actual experiment itself is not so much talked about in the new GCSE spec, but he was the one who said that atoms were made up of a central part of them which contained positive charge, and most of an atom was actually nothing. Particles could pass straight through it if they were small enough, because the gaps between them we're talking about are tiny, atomic size, so very, very small. It's too small for us to see with the naked eye or any equipment we've really got, except for maybe modern discoveries changing that. But in reality, he was the one who said there was a centre to an atom that was made up of positive charge, and the rest of it, the negative electrons, must be whizzing around, occupying very little space at any one time. It was developed by Niels Bohr into this planetary model where you've got the positive nucleus still, and you have the electrons occupying energy levels or shells and moving around. And we're going to come to that atomic structure, the electronic structure, how the electrons are actually arranged in a second, but he said there was an idea of how these electrons were arranged in the shells. It has been taken further by a man called Schrödinger, where it's the quantum model where electrons can be actually at any point, any space at any given time. But it doesn't tend to go that far in GCSE. It can be mentioned, so it's worth being aware of, but essentially that's the development of that model of an atom that we know today. So the numbers of things that you find within the atom. So the number of protons, electrons and neutrons can be found using the periodic table. You do, in an exam, get a periodic table given to you, and I'll show you one similar to which you'll be given in the exam, and you're expected to be able to use that to find out some information. Some of the information you can find from it are the protons, electrons and neutrons. If you look up any element, so this is chlorine, You'll find it in the periodic table with atomic number of 17, mass number, in this case I've given 35. In the periodic table you're given, you could see it's 35.5, but we're going to use 35 for the purposes of this. And I'll come to why exactly I've chosen that in a little bit. The number at the bottom, the smaller of the two numbers, is called the atomic number. The atomic number tells us the number of protons in the atom. Now, if we're talking about the atoms of an element, the number of electrons is equal to the number of protons. And they can ask you about that. They can say, why are all atoms neutral overall? Neutral means they don't have a charge overall in entirety, and that's because they have the same number of protons as they do electrons. If you remember from earlier, all protons are +1, +1, and all electrons are -1, -1. If you have 17 positive things and 17 negative things, they cancel each other out and you end up at neutral, 0. So the reason why all atoms are neutral is they have the same number of protons and electrons, and the two cancel each other out. The number at the top is actually called the mass number. That tells us something else about an atom. That actually tells us the number of protons and neutrons added together. So the mass number tells us the number of protons and neutrons added. So with that information we can find out certain things about an atom. The number of protons is found just by taking the atomic number. So for this, for chlorine, it is 17. It has 17 protons. If you change the number of protons, you change the element itself. Each element has a separate number of protons within it. You can find the number of electrons in an atom because the number of electrons is also equal to the atomic number, i.e. the same as the number of protons. In this case, 17. So 17 protons, 17 electrons. And the number of neutrons, because the mass number is equal to the protons and neutrons added together, you can do a very simple sum to work out the number of neutrons. If you subtract the atomic number from the mass number, you get the number of neutrons. In the case of this, chlorine with 17 protons and 35 protons and neutrons, the mass number, if I do 35 minus 17, I get 18. So this chlorine atom has 18 neutrons. 17 protons, 17 electrons, 18 neutrons. The reason I picked chlorine as this is because chlorine has an isotope. An isotope, defined, is an element with the same number of protons. The atomic number is still 17. It has to be. If you change the proton number, if you change the atomic number, you make a completely different element. So it still has 17 protons, but it has a different number of neutrons. In the case of this chlorine atom, it has a mass number of 37. So if we do the same sum, 37 minus 17, we get 20. This chlorine atom has 20 neutrons, this one has 18. They are isotopes of each other. Same number of protons, but a different number of neutrons. That's what you need to be very clear on when making any statements about isotopes. Same number of protons, different number of neutrons. Okay, and you can calculate the numbers of protons, electrons, and neutrons from these symbols, which can be found on the periodic table that you'll be given. I said I'd come back to the electronic structure and how it is arranged. You can do this for different atoms. I'm going to do one on the little board over here in a second, but the rule for drawing an electronic structure is the 288 rule. It tells us the number of electrons in each of the shells in an atom. So the first shell, the first orbital around an atom, can have 2 electrons, hence the 2 at the start of this. The second shell can have a maximum of 8 electrons. The third can have a maximum of 8 electrons. Now at GCSE you only have to go up to element 20, which is calcium. That does have 2 in its first, 8 in the second, 8 in the third, and actually 2 in the fourth, which we don't really go on to in the 288 rule. The only 2 you will do is potassium, which is shown here, and calcium. Potassium has 1 in its fourth shell, and calcium has 2 in its fourth shell. After that you stop, because the rules change slightly after that point. Don't miss these questions in the exam. okay, they will draw something that looks like this. And I'm going to do one for, say, sodium. So sodium itself, symbol is Na. If I looked in the periodic table, I could find that it had 11 electrons. But on your exam paper will be something drawn like this. And then what you might see, if you look carefully, a little brackets where it says 2 marks, or just a 2 in brackets over by the side of it. A lot of students will miss that question and go straight down to the one that is part B, which has some lines for writing your answer, and then it says like 3 marks over here. Okay? Don't miss these sort of questions. They are easy to get marks on. Don't always look for these lines. Read everything in the question, because there will be information you can gain and there will be marks you can sometimes gain. Anyway, going back to the electronic structure. I've already looked at my periodic table that I was provided with. I've seen that sodium has an atomic number of 11. Therefore, it has 11 protons and 11 electrons. So I'm going to start filling in my shells. Start from the inner shell. How many can the inner shell hold? Well, 2. So I'll put my 2 electrons in the first shell. It's quite often drawn like that with the electrons opposite, but it doesn't matter. You can draw them anywhere as long as you put 2 into the first shell. Is 11 bigger than 2? Well, yes it is. So I've still got electrons left over. I need to go on to the next shell. So I'm going to add electrons 3, 4, 5, 6, 7, 8, 9, 10. Now I've counted to 10 in total because I've included the 2 in the first shell, but a good tip is if you put them in pairs like this, I know when I've done 4 pairs and got to up, down, left and right, then I've filled up that shell with 8 electrons, 2, 2, 2, 2. Okay? So far I've added 10 electrons to sodium. Again, I know it's got 11. 11 is bigger than 10, so I still need to add. In fact, I only need to add another one, 11. Okay? Now that shell isn't full, it doesn't matter at this stage. That is my electronic structure for sodium. I can also check that I've got it correct because at this point I've got 1 in my outer shell. And if I use the periodic table, I'll find sodium in group 1, which is the first column of the periodic table. The group numbers tell you how many electrons are in the outer shell. So I know I've got that right because I've ended up with 1 in my outer shell and it's in group 1, so I'm probably there and I've probably scored 2 marks already. Okay? The outer shell is important because when atoms have a full outer shell, they become unreactive. And again, I'll talk about that in a little bit when I talk about some of the specific groups in the periodic table, such as group 0 is the one with a full outer shell already. So this is the periodic table. This is similar to the one you'll be given in the actual exam. It looks a bit like this. You need to know how to use it. The first thing to notice about it is you don't have a line that you might have seen on other periodic tables, which starts here, this top corner, goes down and across, down and across, down and across, down and across to the bottom of the periodic table. That line is important because it tells us anything to the left of the line is actually metal. All these elements over here are metallic elements, and only the ones to the right of the line are non-metals, which there's only a few of in the periodic table. The majority of elements are metallic. So that's the first thing we can tell from it. A line starting from this top corner, down and across, down and across, down and across, down and across, till we hit the bottom. Everything over here metals, everything over here non-metals. I said about the groups already. So we have groups at the top. Group 1, Group 2, big gap in the middle. This is called the transition metals. Doesn't have a group. Group 3, Group 4, Group 5, Group 6, Group 7, and then Group 0. Okay, we need to know specifics about some of those groups, which I'm going to go on to in a second. But the initial thing you need to know is that tells us the number of electrons that are in the outer shell of those different elements. So everything in group 1 has 1 electron in its outer shell, just like sodium. Anything in group 2 should have 2 in its outer shell. Anything in group 3 would have 3, 4, 5, 6, 7, and so on. Group 0 is called group 0 because it has a full outer shell. Now helium only has 1 shell, but it only has 2 electrons. And that's full, because remember, the first shell can only hold 2 electrons maximum. All the others will have 8 in their outer shell because they'll have a full outer shell, at least up to argon, and that's as far as we need to consider at GCSE. Okay. So that's some of the things we could do with the periodic table. I've already mentioned how you could look at the atomic number, and I can instantly see that carbon has 6 protons. I know that it'll have 6 electrons, so I could draw the electronic structure if needed. I know it should have 4 in the outer shell, and its mass number is 12. 12 take away 6 is 6, so it has 6 neutrons as well as 6 protons and electrons. It's a really useful piece of kit that you should be using in the exam if the information is not given to you. It's one of the most useful bits of kit that scientists have. Again, they can talk about the development of the periodic table. I'm not going to go into in great detail. There are sort of 3 main stages you need to be aware of. You have, I can never say the name, that's really bad pronunciation, but I'm sure you'll get it later on from someone who speaks languages much better than me. But he had a law of triads, which means he groups things into sets of 3. And he saw elements had similar properties, and he grouped them into triads, which means 3, and saw that their properties were similar in those little groups. So he just placed them into random little groups of 3 and dotted them about. Then you've got the law of octaves. So you've got the law of octaves. Newland was the guy who decided that he saw every 8 elements seemed to have similar properties. So he put them in the law of octaves, which was sets of 8. So every 8th element had a repeating pattern to it. But again, he didn't quite make it correct, because although he put them in a sort of order, he sort of mixed up the order. He didn't have anything to go on when he created this, and some of the elements ended up in the wrong places, or some of them didn't fit the pattern of the law of octaves. The actual person who came up with this suggested structure, it wasn't quite complete when he suggested it, was Mendeleev, Dmitry Mendeleev. He actually suggested that the periodic table was in order of accreasing atomic mass. Now, he didn't know about atomic number at that point, but it was later found that atomic number, the number of protons, was the order it should be in. But he suggested mass originally, and when he put them into that order, he started finding that there was groups, columns, that went down where elements had similar properties. They acted similar to one another. And that was kind of the accepted structure. Now, what was so clever about his discovery was he actually left gaps in his periodic table. When he put together his structure, he left spaces, and he actually used his knowledge of this repeating pattern to predict what that they hadn't found elements yet, and elements would be found to fill these gaps, and they would have properties similar to the elements they were in a column with. He suggested that. And that's what made his discovery different to other people who had come before him. He actually left gaps and made predictions about what elements would be discovered to fill those gaps. And years later, it was discovered that he was correct. It shouldn't have been in order of mass, and there was some change there, but he did actually bend the rules slightly to make it work with the patterns, and it was actually found that he did have the majority of the order correct and left the gaps in the right places, and elements were later discovered that filled that. So that's the periodic table. There are some specific groups you need to be aware of in the periodic table. Group 1 is called the Alkali Metals. It's the first column of the periodic table. These metals, they're all metallic, and the reactivity increases as you go down the group. So as you go down from lithium, sodium, potassium, rubidium, cesium and francium, they get more reactive. They get more reactive as you go down. And the reason being for that, and I'm not going to go into great detail on this, but it comes down to 2 things. It's called distance and shielding. When group 1 reacts, such as sodium, they want to lose this outer electron to get a full outer shell inside. So they want to lose that electron. And it's easier to lose that electron if it's further away from the nucleus, which, remember, the nucleus is positive because there's protons in there, and electrons are negative, so they're attracted to that. The further it was away, the easier it is to lose those electrons. That's called distance. And also, the more electrons that were inside of that outer electron, they shielded that outer electron from the effect of the nucleus. That's called shielding. So distance and shielding is why as you go down the group, they get bigger and there's more electrons inside. That's why they get more reactive as you go down the group. An example of a reaction that they talk about is the reaction of group 1 alkali metals with water. An example for sodium, such as the one over there, is sodium reacts with water to give sodium hydroxide and hydrogen gas is released. If we did it for another group 1 metal, such as lithium, it would be exactly the same, except we just replace the word sodium for lithium. So lithium plus water gives lithium hydroxide and hydrogen, and so on and so forth. I'm not going to go through each one. That's the general reaction. For sodium, you just replace the metal for whatever alkali metal, group 1 metal you're talking about, and they get more reactive as you head down the group. Another group you need to be aware of is group 7, the halogens. Group 7, the halogens, are found over here: fluorine, chlorine, bromine, iodine and acetine. With those, the reactivity increases as you go up the group. So fluorine is the most reactive and acetine is the least reactive. Additionally with this, the melting point and boiling point increase as you go down the halogens. These two are gases at room temperature, and they have really, really low, in minus numbers, melting and boiling points. Bromine is a liquid at room temperature, which turns to a gas quite easily around room temperature. Iodine is actually a solid at room temperature, and so would acetine be if we could obtain a sample of it, but it's not very stable itself. So, as you go down, the melting points and boiling points increase. Another pattern you see going down the group is they get darker. Fluorine's very light, chlorine's getting darker but still very light, a greenish gas. Bromine's a brownish liquid, iodine's a really dark purple solid, and acetine, again, if we had a sample of it, would be like black, very black and very dark. They get darker as you go down the group in terms of colour. So most reactive for the top, at the top, least reactive at the bottom, and the reason being is the opposite. Group 7 have 7 in their outer shell, and they want to gain electrons. When they gain electrons, it's easier if they're smaller, because they can grab electrons easier because it's closer to the nucleus in the centre. Whereas iodine, which is big, the electrons it's trying to grab are quite far away from the nucleus in the centre, and it makes it much harder for it to grab hold of the one electron it wants, and therefore it's less reactive than fluorine. Okay, so distance and shielded again. Smaller, less electrons on the inside, which makes it easier to grab electrons. Opposite over here, it wants to lose electrons, so small means bad because it holds onto those electrons more tightly. So more reactive down here than up here, more reactive up here than down here. Okay, so it's the opposite. A reaction they might talk about for group 7 is called a displacement reaction. It's where you displace or just replace one element with another in a compound. So this is chlorine. This is elemental chlorine. We can tell it's elemental. It's in its elemental form because it ends in I-N-E, ion, chlorine. Whereas over here we've got potassium bromide. Bromine is in a compound. We can tell it ends in I-D-E, ide, bromide. Whereas, because chlorine is more reactive than bromine, it will displace or replace the bromine in the compound. So you get the products, potassium chloride and bromine is released. You see the chlorine and the bromine have swapped positions in the products. That only works if the element you've added into the compound is more reactive. If you were to add bromine to potassium chloride, no reaction would take place because chlorine is higher than bromine, therefore chlorine is more reactive, so chlorine would stay in the compound and bromine can't displace it. Elements higher up displace, elements lower down do not react. Okay? Group 0, last one you sort of need to know a bit about. Not too much you need to know about them. They're called the noble gases. They're very unreactive because, as you've probably guessed, and I said earlier, they have a full outer shell. Atoms are happy when they have a full outer shell, so they're unreactive at that stage. They're monoatomic, which means they're generally made up of single atoms. If you look at helium, helium is an element where you just have single atoms of helium, not joined to anything else. It's happy to be on its own. Similarly with neon. Neon is happy to be on its own. They're all gases at room temperature, so they are all gases at room temperature, but if you were to look at a pattern of the melting and boiling points, the melting and boiling points would get higher. They're all negative, they're all below zero, but they would get higher as you go down the group, just like in this group, except here they all stay as gases at room temperature. Moving on to another topic, chemical calculations. It's something that a lot of people do struggle with. It is a maths aspect of chemistry, and it will crop up in some form during the paper. There are some bits I'm going to go over, but there's some bits I'm just going to skip right past, simply because you could spend a lot of time working on this aspect of chemistry. But if you're not able to do the maths at this point, you're really not going to be able to do it after practicing it just over tonight. And it's generally only going to be worth a few marks. So I'm not going to spend too long going on about it. I'm just going to tell you the basics of how to do it, and I'll leave some bits up for us to think about it, to take it a bit further for those who want to. So there are two sort of terms you need to be aware of. One's relative atomic mass, often given the symbol AR. This is the mass number from the periodic table. It is the mass of an element as compared to carbon-12. When they decided this, they decided everything in the periodic table would be based on carbon-12. So the mass of any element is based on that. If I go back to the periodic table, I know it's probably very hard for you to see on the screen. If you've got the notes, you'll be able to see it clearer. You will get a clearer one of these in the exam. But if I was to look at sulfur, sulfur's mass is 32, and that's compared to carbon-12, carbon being 12. Everything was compared to carbon-12. But the mass number tells us the relative atomic mass of different elements. The relative formula mass is given a symbol MR. It's a little bit more tricky, but all you need to do is the mass of the compound, which is found by adding up the elements that make it up. So again, you might be given them in the question, but if not, you use the periodic table, you look at the masses of the elements that you have in the compound, and you just add them together. Okay? I'm going to give you a few examples of that, because this is something that we all should be able to do. This one is magnesium chloride. So if we've got magnesium chloride, the formula for magnesium chloride, which would be given, is MgCl2. Now, to work out the relative formula mass, or relative molecular mass sometimes called, the MR, you add up the elements in it. So I'd use my periodic table. I'm looking at it now. I can see that the mass of magnesium is 24. So 24. Then I look what numbers come after the magnesium. I'm looking at the little numbers. If there isn't one present, but the element's there, that means there's only one of that atom. So I do 24, because I could put a little 1 in here if I wanted. Chemists are generally lazy, so they don't want to put 1s in things, but you can do. You're not going to lose marks if you do. But the mass of it is 24, and because there's only one of them, I times that by 1. And I'm going to put some brackets around it, because that's magnesium dealt with. Okay? Then, I'm going to add to it the mass of chlorine. Now, chlorine, over here, has a little 2 after it. So if I use my periodic table, and again, go to my periodic table, and I look, and this is one of the ones I said, you might see chlorine is 35.5. So, using chlorine as 35.5, I would put 35.5, but because there's 2 of them, multiplied by 2, and put it into brackets. Now I like to be thorough when I'm doing these calculations, so I'm going to resolve the brackets before adding them together. That means I'm going to do the sums in the brackets before going any further with it. So 24 times 1 is just 24. Okay? Plus 35.5 times 2 is 71, if my maths is correct. Then I just need to add the two numbers together. So adding them together, I'm going to get 95. Again, if my mental maths is okay. I'm not too worried about that. It's the process of how I do it that's important at this stage. Mr. Pritchard's given me the thumbs up, so I'll take that as a yes. So that's magnesium chloride. You find out the masses of the elements in it, and you multiply it by the number of those elements that are in there, and you add them together at the end. It can get a little bit more tricky when brackets in formulae get involved. So this is calcium hydroxide. It has a brackets in the formula. But just like in maths, you do the brackets first, then you multiply it by what's outside of the brackets, then you add them all together. So brackets, multiplication, and then addition. Not dissimilar to what you might do in maths. They call it something funny like big maths or something like that. I'm just worried about you know how to do it. So for this one, calcium hydroxide. Again, I'll look in the periodic table and I'll look at calcium and I'll go, calcium here has a mass of 40, so I'll write that up, 40. And again, I'll be thorough, so there's no number after this, so it's times by 1. Now it gets a little bit more tricky because I have to do this brackets bit over here. So I've got oxygen and hydrogen in the brackets. So here, I'm going to put plus, I'm going to open some brackets, but I'm actually going to open a second set of brackets for what's on here. Oxygen, look in here, it's got a mass of 16, plus hydrogen, which has got a mass of 1. That's my bit inside the brackets, but the reason I've got a second set of brackets is because now I need to times that by 2. And that's my actual equation. Again, I'm going to be thorough in doing it, so I'm going to resolve the first set of brackets first. Now, don't be worried about spending a bit of time on it. So I'm going to leave this as 40 multiplied by 1. I'm not going to do anything with that first. And then I'm going to do 16 plus 1 to give me 17 times by 2 over here. Okay. Then I'm going to take it the next step, resolve those bits. So I've got 40 times by 1 is 40, plus 17 times 2 is 34. And finally, my sum, 40 plus 34, should give me 74. Okay. So I've worked out the mass of calcium hydroxide. Okay, those bits are okay. Doing those calculations is not too bad, working the relative formula mass. And they can be worth up to 3 marks in an exam if one does come up. So it's worth being able to do that, and that's just a bit of basic maths to do. Conservation of mass. Okay, the law of conservation of mass states that no atoms are lost or made during a chemical reaction. What you start with, you end up with. A simple analogy for this, for me, would be these 2 pens. Okay, if I was to do a reaction with these 2 pens, I've got a black pen with a black lid and a red pen with a red lid. If they were to react together, what might happen is they might swap their lids. Okay, and I've made 2 new pens. I've made a black pen with a red lid and a red pen with a black lid. So I've made a new product. Okay, my reactants are what went in, and this is my product. The number of the pieces that make up my products is the same as the pieces that made up my reactants. I haven't lost or gained anything. It started as 2 pens with 2 lids. It finished as 2 pens with 2 lids. No atoms can be made or lost during chemical reactions. And this is what comes down, this is what is important when balancing equations. Okay? What it also means, it means the total mass of reactants must equal the total mass of products. So if I know how much all the mass of my reactants is, it will be the same on the other side of the arrow. Chemists use arrows instead of an equal sign, but it will be the same on the opposite side of my arrow to what is on the left side. So left and right will have the same mass if we weighed it. Now, a few people ask me about balancing equations, and I say this to students all the time. I could spend the entire hour and a half teaching you how to balance equations. Some of you would get it by then, some of you probably still wouldn't. I could spend another week doing it with you, and some of you might be there, and some of you might still not. It's going to be worth 1 or 2 marks in an exam. The trick is, give it a go, don't spend longer than 1 or 2 minutes on it, and move on to the next one. Don't worry about not being able to do it. For some reason, students seem to think that the balancing equations makes you a chemist. Okay? I didn't learn how to do it properly till I was well into my A-levels, if not partway through my degree, and it just came through practice of doing it. In reality, it's not worth many marks, it's not worth stressing about spending too long on it. In this equation though, we might be given an equation like that. So this is magnesium reacting with hydrochloric acid to give magnesium chloride and hydrogen gas. I might be given that equation, and quite often what they'll do in an exam, if they're asking for balance equations, is they might do something like this. They might give you parts of it. So magnesium plus hydrochloric goes to magnesium chloride plus, and they might have a line for you to write something here, because they might not give you one of the products. They also might have lines in front of the different things that are in the equation. If they have something already there, like an element or a compound, on that line you are not sticking different elements or different like compounds. I've seen like iron just added into random equations and carbon just stuck in for seemingly no reason whatsoever. Okay? These lines in front of elements and compounds, all they're looking for is a number. They just want a number. And some of them might not even have a number, because, as I said, chemists are lazy. If the number's 1, we don't even write it. Now, you could write it, not lose any marks, but in reality, you don't have to with 1s. If there's a line after a plus or before a plus and there's nothing written there, then they are expecting you to add something in. And what you've got to think about is you've got to think about the law of conservation of mass says that the same things on the left of the arrow must be on the right. So what's missing? Well, I've got my magnesium, I've got my chlorine, no hydrogen whatsoever. So it's got to be hydrogen there. Now this is where it gets a little tricky, because you have to know that hydrogen is what they call diatomic. It exists as H2. Just like oxygen only exists as O2. So I'd have to put H2 after it. That takes a bit of prior knowledge, but it's something that you might be able to do. At that point I've got 1 out of the 2 marks, and the last mark is for making sure that I've put the numbers correctly in front of the different things. So, magnesium, okay, what I'm going to do is I'm going to look at how many magnesiums I've got on the left and how many I've got on the right. Magnesium, I've got 1 on the left and I've got 1 on the right. So that all looks good at this point, okay, no problems there. Okay. Chlorine, I'll go to chlorine, I'll ignore hydrogen because I added that in. I'll go to chlorine, I've got 1 over here, and I've got 2 over here on the right side. So that's instantly not working. Now the last thing you could do, you cannot do this ever in equations. You can't just go on and stick a little 2 here after the chlorine, that's going to work and everything's going to be fine. You can't change the little numbers. You have to put big numbers in front. And the big number means everything after it is multiplied by that. So in the case of magnesium, I could have gone, well, there's only 1 magnesium, so I'm going to put a 1 here, because there's only 1 magnesium over there. And that would have been fine. You don't have to, but it would be fine. For this one, though, I already know I've got 1 chlorine over here and 2 chlorines. If there's a little number attached to it, it means only that is doubled, not the magnesium. There's 2 chlorines over here. So to fix it over here, I need to put a big 2 in front of that. That also means I'm doubling up the hydrogens. I've got 2 hydrogens and 2 chlorines now. But that works for the chlorines. I've got 2 there and I've got 2 here. And hydrogens, last of all, the one I added in. Well, this is H2, so this is already 2 hydrogens. And I've put a 2 in front of here, so this is 2 hydrogens. So it works. So I know I only need 1 of those and 1 of those. Now, as I say, I've gone through it quickly. Okay, that is a relatively simple one. Well, it's not actually. There's 4 things in it. You had to add something to it. If you don't get it now, we're not going to stress about it. We're going to move on. We're going to forget it. We're going to go, that's 2 marks I might not get in the exam, but that's okay. Because if I get 68 out of 70, I've done pretty well. We're not even really looking for that in reality, but let's just get the marks we can. So I've balanced my equation, and if I know the masses of certain things, if I knew that I had I'm just making up these numbers, by the way, they don't actually work. If I had 50 grams of magnesium and I added it to 50 grams of hydrochloric acid and I made 25 of hydrogen gas, how much magnesium chloride would I make? Well, I know I've got 50 of this and 50 of this, so that makes 100. Over this side, I know I've got 25 already. It needs to add up to 100, so 100 minus the 25 I've already got equals 75 grams. I have 75 grams of magnesium chloride. That's a simple one if you're given the masses of some different things in equations. Now there is one called a reactive mass calculation, which is difficult, which I will show a little bit, but I'm not going to go into detail on again. With this though, the problem would be with this reaction, if you were to do it, it's creating hydrogen, and hydrogen is a gas. If you actually put this on a balance and did this reaction, you would add magnesium, which is a metal, a solid, into hydrochloric acid, which would probably be in solution in a beaker. You would add that in and it would weigh 100. Now when the reaction had happened and you got the products, it would probably, if you left it on a balance, only weigh 75 grams. And you might be thinking, why? The conservation of mass says that what I put in, I should get out. And it's because one of my products is a gas, and that gas will float away. So anytime you're producing a gas, such as hydrogen, the mass will appear to get lighter. And that's because you're not weighing the hydrogen that's produced. It's the same if you were producing carbon dioxide. You wouldn't be weighing the carbon dioxide that's produced. It would appear to get lighter, but really the amount you put in should equal the amount you made. Moles. Moles are something that's been added to chemistry in the new specification. Well, they've always been around. They're an important thing for chemists to be able to use, but doing calculations on them, we need to go into a little bit more detail. I'm only going to give you the formula, and again, a very brief overview of it, because if you can apply this formula, then you can do most of the calculations. So the number of moles of a substance, and a mole is just a measurement that chemists use to represent an amount of a chemical. So don't get hung up on the word. It's not talking about a small furry rodent, it's just a measurement. Okay? The number of moles, the amount of a chemical you've got, if you think about it that way, is equal to the mass of the compound divided by the relative formula mass that you might have calculated. A question like that might follow on from a question where you've just calculated the relative formula mass. It might say, if I have, what could I have? 148 grams of calcium hydroxide, how many moles would I have? So if I did 148 divided by the formula mass I've just calculated, 148 divided by 74, I could work out the number of moles I would have of calcium hydroxide. So it might be a follow-on question from where you've just worked out the relative formula mass. How many moles of calcium hydroxide is that? You just do the mass, divided by the formula mass, it will tell you the number of moles. Again, they could follow it up with another calculation. It's using a thing called Avogadro's constant, which is a funny number. It's 6.023 times 10 to the power 23. You are expected to be able to use standard form in the science GCSE now, so you'll get a number like that. And it might tell you how many particles of that substance are there. Well, this number is the number of particles you get in 1 mole of any substance. Doesn't matter what it is. If you've got 1 mole of carbon, you've got that number of particles. If you've got 1 mole of oxygen, you've got that many particles. Okay, so to work out the number of particles you've got, you just do the number of moles that you might have just calculated multiplied by Avogadro's constant, 6.023 times 10 to the 23. That will tell you the number of particles you've got of that substance. So that's using moles. Concentration is another one that's been added to the GCSE. Now I'm not talking about concentrating in your exams, I'm sure you're doing that already, but you have to calculate the concentration of a substance, which is the concentration of a solution is a measure of how much substance or solute is dissolved in a certain amount of solvent. The units usually are grams per decimetre cubed in GCSE chemistry. Okay, that means decimetre cubed is a way chemists use instead of litres, so that's 1 litre, which is actually 1,000 centimetres cubed. The units conversion, you may have to do that. 1 decimetre cubed is 1,000 centimetres cubed, so you need to get it in the right units. To do your concentration is equal to the mass in grams divided by the volume in decimetres cubed. If you do that, you'll have the concentration of your solution. Again, it's just a formula you have to be able to use. You may be given it, but you need to be able to apply it. This is up there. Now, it's a reactive mass calculation. I just wanted to show you sort of things. So this is a reaction they'll give you, and they'll actually tell you that a company has made magnesium, which is this, using this reaction. Calculate the mass of magnesium oxide, which is this over here, to produce 1.2 tonnes of magnesium. The only tips I'm going to give you for that is you ignore the silicon and the silicon oxide, you ignore the things they don't talk about, just forget those. You work out the mass, the total mass of magnesium oxide, including this 2, so you do 2 times whatever the formula mass of that is, that you'll have to calculate. You work out the total mass of magnesium, which is just an element, so you'll get that from the periodic table, but you have to times it by 2. And that will tell you that this amount of magnesium oxide will produce this amount of magnesium. You then divide both by the number you want to get to 1. So essentially you want to know the amount that 1 gram will produce. You divide them both by the amount of magnesium oxide to get 1 gram of that will produce however many grams of that. And then you multiply it up by the number of, well, this is tons, but the units don't really matter. Tons or grams, it works the same. This sort of thing though, that's as much as I'm going to say on it, it's the sort of thing that if you really want to know how to do, that's what I'd suggest you come in the morning and ask me. But again, look at this, it's worth 3 marks and it's actually a really complicated process to get it right. So maybe we don't sweat that too much. If it comes up, we'll deal with that. Bonding, okay, huge topic, guaranteed to come up in some form, so I need to go over it in a bit of detail, but again, won't be able to go into everything. Okay? There are 3 types of bonding you need to be aware of. Ionic bonding, which occurs between a metal and a non-metal, and it's where electrons are transferred. The metal always gives away electrons, and the non-metal always receives electrons. They both end up with a full outer shell, and they both end up happy. Okay? So, ionic bonding between a metal and a non-metal. And remember, we can find out what's metals and non-metals using the periodic table. Covalent. That occurs between non-metal and non-metal. So if you've got 2 non-metals joined together, or just the same non-metal joined to itself, that's covalent bonding. And in this, electrons are shared. It's friendly bonding. They share the electrons together, both end up with full outer shells, and they're happy. And then metallic bonding. This occurs in metals. It could be 2 metals joined together, or it could just be 1 metal bonded with itself to make up its structure. The way the structure is for this is it is positive ions, which are positively charged particles, with a sea of delocalized or free electrons, which are able to move around. They're like a glue that holds it together, because the positive and negative attract each other, so they stick together, but also they're able to flow. And that's important for a later bit we'll look when we look at metallic bonding in a bit more detail. So for ionic bonding, you can be asked to do what's called a dot and cross diagram. That can involve all the electrons in 2 elements, sodium and chlorine in this example, or it can involve just the outer shell electrons. Look at what the question's asking you and use that. Read it carefully. So sodium, the electronic structure is that, we did it earlier. Chlorine, the electronic structure is this. I know that sodium has 1 electron in its outer shell because it's in group 1, and chlorine has 7. They both want to get full outer shells. They can do that easily by sodium giving away its 1 electron and chlorine taking the 1 electron. The reason you use crosses for one and dots for the other is so you can clearly see that that electron used to belong to sodium, but it gave it away and it's now on chlorine. So you can see where that electron's come from. When you do your dot and cross diagram, if you expect to do this, you now need to put square brackets around each of the different elements in the compound. The reason being is because they're no longer atoms, or just atoms, they are ions. They have a charge. This one has a positive charge. I know it's probably very blurry on the screen, but this has a positive charge because it's lost electrons. Electrons are negative, so if this is an electron and it's negatively charged, if I give it away, I'm going to be more positive because I've given away something that's negative. Similarly, if I'm chlorine and I receive something that's negative, I'm going to feel more negative now because I'm carrying something that's negative with me. So if you lose electrons, you become positively charged. If you gain electrons, you become negatively charged. Properties, what they're like, that means how they are. You may need to talk about this. They form, this is their structure really, a giant ionic lattice, which is a regular arrangement of negative and positive, negative and positive, negative and positive. It's 3D as well. I can't show that easily on a board, but it would go back into the board, come out of the board. And it's giant because this would go on for millions of atoms in an area. The positive and negatives are opposite charges, and as we know, opposites attract each other. Because it's a giant ionic lattice and it's a regular shape, it forms crystals, it's crystalline. Sodium chloride is what you might know as salt, table salt. And it forms crystals. If you look at it under a microscope, it's actually crystals. You might be able to see them at home. It's held together by strong electrostatic forces. Now that sounds like a complicated term. Really it just means electric charges, positive and negative, which don't move, static. And electrostatic forces is just the attraction between a positive and a negative. That's what holds it together. And because it's held together by electrostatic forces, which are really strong, the attraction between a positive and negative is really strong, it means that it has a really high melting and boiling point. It takes a lot of energy to melt them or to boil them. They do not conduct electricity when they're solid, because even though they have positive and negative things, which usually can carry electricity, when they're solid, they're locked in position and they can't move anywhere. Because they're locked in position and can't move, they can't carry electricity, therefore it can't conduct. But what could we do? If we heated it up enough, we could actually cause it to melt, and the ions would be able to move over each other and flow and move about in a liquid. If they do that, they can then carry electricity. Another way that they can carry electricity, if we don't want to melt them, because I've already said they've got high melting and boiling points, so that's a lot of energy we would have to supply to melt them, is we can actually dissolve them in water. If we dissolve them in water, they conduct. So they do not conduct electricity when solid, but they do conduct electricity when molten or in solution. Covalent bonding. Covalent bonding, there's actually two types of covalent substances we need to know about. Simple molecules and giant structures. Okay? Giant structures, the ones that they go on about, diamond, graphite, silicon dioxide and fullerene. They may talk about, one they quite like at the moment, it's like the flavour of the month, is graphene. Graphene is, when I talk about graphite, graphene is the same, it's just a single layer, one atom thick of graphite. So that makes it good, it has the same properties of graphite, which I'll go into, but also because it's only a single layer, it can be transparent and it can be flexible, which makes it really good for things like mobile phone screens and things like that, rather than the glass we actually use currently. The problem with it currently, graphene, is it's quite expensive, so that's why they don't use it so much at the moment. Anyway, simple molecules, not too tricky. Now you can draw dot and cross diagrams for covalent compounds as well. Again, that's going to be another thing though that I'll leave. If you want to speak to me about it in the morning, that's fine, but in reality, it takes a bit of practice to get doing. There's a few that come up quite regularly. These are some, they're not all of them, there are more, but hydrogen chloride, hydrogen with chlorine, you only show the outer shell electrons, and what it is they should have at least a pair of electrons, one dot, one cross, in this bonding area in between them. There's a question, looks like, from Mr. Pritchard.
We do have a question. It's from Louis. Is sharing outer shells in chemistry on paper 1? If so, is it possible if Mr. K could go through an example, please? Just one example.
Of covalent bonding, sharing electrons. Okay, I'll go through one example then. As I say, it is a bit tricky. It takes a bit of practice. But I'll go through one example of how to do it, and then we'll move on for there. So thank you for your question. Right. We can do it for water, which is shown up here. So we'll do it for water. Now, generally in your mark scheme, in the paper, what they'll give you is they'll give you it drawn out. They won't make it really hard. You'll have something like this already drawn for you. And what you'll notice, it will be like circles that are overlapping. The overlapping sections are where the bonds are, and the bits that are not overlapping, they're just the orbitals, that the electrons that are not shared. What you need to do is you need to look in the periodic table how many electrons are in the outer shell of these different elements. As you probably remember, we find that from what group they're in. So oxygen's in group 6. That means it has 6 electrons in its outer shell. I'm going to use red crosses for it. The first thing I do is I put a cross in one of the bonding areas for oxygen. I do the same in the other. It will always add sort of 1. There are a few examples that I'm not going to go into where it might not add anything to this area, but let's go on the proviso at the moment, the idea that it will add 1 electron to each of the bonding areas. So I've done that, 1 to each. For oxygen we said had 6. If it's used up 2 of that 6, it's got 4 left over. The 4 is greedy with it, doesn't share. So I'm just going to put them just on the oxygen in that area up there. Then I'm going to move to the hydrogen. Now hydrogen only has 1 electron full stop. So I'll put 1 dot in the bonding area here. If I've used the 1 electron from hydrogen, it's got no more to keep just to itself. It's used its 1 electron in the bond. Similarly over here, I do the same for this hydrogen. Put 1 dot in the bonding area. It's got none just for itself, so therefore it's got nothing left just on the outside. At that point, I should have it right, but I'm just going to check. What I need to know is has each element got a full outer shell? We can consider any one we like first, but let's consider oxygen. So I'm going to count the total number of electrons that are around oxygen, remembering that it's got more than 1 shell. It's actually got 2, so it wants 8 in that shell. So I've got 1, 2, 3, 4, the 4 it had just to itself, 5, 6, 7, 8. It has 8 in its outer shell, it's now happy. If I cover up the oxygen, I do the same things for hydrogen. But for hydrogen, I've got to remember that it only has 1 shell, therefore it only needs 2 electrons to be full. 1, 2, yep, that one's happy. 1, 2, this one's happy. I know I've done my diagram correctly. The tricks are looking at the number of electrons that are in the outer shell, putting 1 in the bonding area for each atom that are there, and then the rest that are left over just go belonging to the atom themselves. Again, don't miss those questions. There'll be rings like that, and then like 2 marks by it, and then marks you can't get. So, simple molecules they are. They're simple because they're only made up of a few atoms. And then we need to know a few bits about them. They never conduct electricity. Because they're sharing electrons, they're overall neutral. So therefore, the atoms themselves, I hope we didn't lose the feed there. It looked like we were running out of charge on our video, but hopefully we're still all right and you're still with me and we can carry on. So what I was saying is, they never conduct electricity because they don't have any charge. Because the electrons are shared and not transferred, these atoms, the overall molecule, is neutral and there is no charge associated with it, so it can't carry electricity. Just going to stop from here before I carry on. Are we good to go? We lost the feed?
We lost the feed, yeah.
Okay.
Same street happened, we can't see anything, can't see you.
Okay, so probably might be able to hear me, but not see anything at this point in time. We're trying to sort out those technical difficulties. Hopefully we'll be back up and running. What I'm going to do, if you can't hear me, is I'm going to pause my little timer so we still get the full hour and a half. We're about an hour in, half an hour to go, still lots to cover. Right,
Okay.
hopefully we are live again. Little interruption there. This is what makes it exciting for me and for you, I'm sure. And we'll pick up where hopefully we left off. And I was talking about simple molecules. So I'm going to go back to the start with that. Hopefully you got the bonding diagram before we went. And we'll talk about simple molecules just now. So, simple molecules never conduct electricity because they have no overall charge. The molecule itself is neutral. Because it has no charge, it can't conduct electricity. They never will. So simple molecules never conduct. They have low melting points and boiling points due to weak intermolecular forces. Now, I could go into a lot of detail on what that is, but for now, let's just sort of say that it's the forces between the molecules themselves. So, not the bond is strong, but between this water and another water, there's a weak force holding them together, which makes them have low melting and boiling points. So when it comes to simple molecules, you need to remember that bonds are strong, ion forces are weak. Okay? So that's something that we can remember about them, and that's why they have low melting and boiling points. In terms of giant covalent structures, I'm going to talk mainly about diamond and graphite. Fullerenes and graphene share similar structure to graphite. So if you've got questions about those, which may well come up, remember they are similar to graphite, and everything I'm about to tell you about graphite applies pretty much to fullerenes and graphene as well. Graphene has the added extra bit that it's transparent and flexible, which makes it great, but essentially it works the same way. And fullerenes can be arranged into balls or into tubes, which can be very strong and useful for a variety of different things, such as drug discovery or reinforcing different bits and pieces. But the main two I'm going to talk about are diamond and graphite. Okay? These may come up. Both are made up of carbon atoms. They're only made up of carbon atoms. They're really, really strong structures generally. Diamond is a bit stronger than graphite. But they have extremely high melting and boiling points, which means you need to supply lots of energy to break the covalent bonds that are in them to actually melt them. And they are in a giant structure. These diagrams only show a really little bit, but are actually millions of atoms, again, like the Ionic, joined together to make a giant structure. The key bit about diamond is that each of the carbon atoms is joined to 4 other carbon atoms, and that makes it extremely hard. The way I remember that is if I asked you to draw a diamond shape, you might draw a shape sort of like this, which has 4 points to it. And those 4 points tell us that diamond has 4 bonds. The melting point and boiling point are incredibly high, and it's really, really strong. One of the toughest naturally occurring materials known to man. One of, not the toughest necessarily. It does not conduct electricity though, and I'll come back to exactly why that is when I talked a bit about graphite. So graphite has only got 3 bonds. It's still made up of carbon, but each of those carbons has 3 bonds, which actually leaves a free electron. So 3 bonds give it a free electron. And that free electron can actually move around. And that free electron is the thing that can carry electricity with it and actually cause it to, oh, didn't restart my timer, so just going to do it now. So that free electron that's able to move can carry electricity through the structure, and actually means that graphite can conduct electricity. Also, graphite is arranged in layers, and those layers can slide over each other, and in some cases can actually break away from each other. And that's why graphite is actually used in pencils. When you rub a pencil across a piece of paper, the layers break away and they're left on the page, and that's what you can see. So these layers are held together with weak intermolecular forces, and they can actually break off and come apart. It's also, the layers allow the layers to slide over each other, and that means it can be used as a lubricant for machinery, for machine parts, to stop them rubbing against each other, to help them slide over each other and not get broken. Key thing though, really key, same with graphite and with graphene and fullerenes, are they have 3 bonds, so they have a free electron which can carry electrical charge, which means it conducts electricity. A tip for you is, if you cannot remember anything I've said, but you do a question's asking you why does something conduct electricity, a good answer is it has free electrons which carry charge. That can score you 2 marks, so it can come up. It's just something to put down if you can remember nothing else. Okay? Whereas diamond, because it has 4 bonds, as we said earlier, doesn't have any free electrons, so cannot conduct electricity at all. So diamond does not conduct, whereas graphite has a free electron and conducts electricity. Oh, I didn't mention it. I said that fullerenes and graphene are similar to graphite. Well, silicon dioxide is very similar to diamond, except it's made up of silicon and oxygen together. But in terms of the number of bonds, 4 strong bonds between the silicon, and it's really hard material because they're strong covalent bonds with a high melting and boiling point. Metallic structures. Metallic structures, as I showed you, are a bit different. They're positive ions surrounded by delocalized electrons which are free to move. Those delocalized electrons can carry charge throughout the structure. So metals, again, have a giant regular lattice, which makes it have a really high melting and boiling point, and also has a crystalline structure. It's, again, just like Ionic, held together with a strong electrostatic forces, which means it's got this high melting and boiling point, but it also conducts electricity due to, you guessed it, free electrons carrying charge. Okay? They can be bent and moulded into shape. Because they're in layers and these layers can move over each other, you can bend a metal into shape. That's called being malleable. It can be bent and moved into shape. If you want a metal that's a bit tougher, so you want something to do a job that needs to be really strong, what you can do is you can actually make it into an alloy. If you make it into an alloy, you actually add in atoms that are a different size to the metal atoms, and they actually disrupt these layers and mean it can't actually slide over each other, and they make it stronger and much tougher. An alloy that used to come up in the old spec, may not come up in this one, was a shape memory alloy that could actually be used to return to its certain shape in different temperatures. Okay? But essentially for an alloy you have different size atoms which disrupts the layers and stop them sliding over each other. So moving on, acids and bases. Okay? Acids and bases are measured using something called the pH scale. Acids are down at the lower end from sort of 1 to 6. They are acidic pHs, whereas 8 to 14 are alkaline. Now I use the words base, acids and bases. A base is a substance which neutralises an acid, and if you dissolve that base in water, you make an alkaline solution. Acids are acids whether they're in water or not, but there is something you need to know about them when they're in water. You can get these colours, red, yellow and orange, and then this is supposed to be purple and dark blue, by adding universal indicator to them. That's what gives the colours. A key thing, something that comes up with fairly often, is all acids, when you dissolve them in water, release H+ ions. So if any question asks you why is something acidic, or why is this solution acidic, you'll bet it's because it's got H+ ions dissolved in it. Okay? Similarly, all alkalis release OH-. You can put the minus anywhere, but generally you put it on the oxygen, so OH with a minus. Okay? So all acids have H+, and all alkalis have OH-. Now if you add together equal amounts of H+ and OH-, you add them, you actually make, we've got 2 hydrogens and 1 oxygen, H2O, which hopefully you recognise as water. So if you add an acid to an alkali in equal amounts, you make water. And water has a pH of 7, neutral. So actually, any neutralisation reaction, this is called the Ionic equation for a neutralisation reaction, H+ plus OH- goes to water. That's what you can write out for any neutralisation reaction. That's the Ionic equation that's going on. I call it an Ionic equation because it's showing the ions, the positive and negative ions that are involved in it. If you're doing that, and you're adding these two things together, you might do what's called a titration. This is added to the new GCSE spec. It's actually a practical they can talk about. With it, a titration involves a piece of equipment called a burette, which is like a long glass tube that stands up and you clamp it on. And underneath it, you have a conical flask which contains an acid or an alkali. In this case, the conical flask will contain the alkali, and the burette, which is the tube that stands up on end, contains an acid. The burette has a little tap on the end of it, and what you do is you actually open up the tap and it releases the acid into the alkali. And it also, the burette has measurements on it which tell you the volume of acid you're actually adding. 1 centimetre cube, 2 centimetres cube, 3 centimetres cube, so on and so forth, adding the acid. Okay? What you can produce from that, if you're taking measurements of the pH of the solution, which you can do using a pH probe, which is a piece of electronic kit that actually tells you the exact pH of the solution that you're measuring. Initially, just in your flask, if you've only got alkali, you would have a high pH. This is around 12.7 or something like that. Doesn't matter exactly. As you start to add the acid to your alkali, it will begin to neutralise some of the alkali in the flask. And the concentration of H+ ions, because actually, should have mentioned that the concentration of H+ ions being high gives it a low pH, whereas the concentration of H+ ions being low gives it a high pH. So this is due to the amount of H+ ions, the acid, that are in the solution. If there's a high concentration, the pH is low. If it's a low concentration, the pH is high. Now that may seem a bit backwards, but that's the measurement of pH. And also in the new spec, they do say that if you go up by 1 pH unit, you've gone up by about 10 times the concentration of H plus ions. So if I had, let's say, well, this is going down essentially. If I had 100 here, I would only have 10 by here, and 1 by the next, and so on and so forth. So anyway, I'm adding in my acid, and the pH has started to fall. My pH has started to drop, because the acid is neutralising the alkali, and the pH is starting to fall. At this point, you want to go straight down. This is the neutralisation point. This is when I've added exactly the right amount of acid to completely neutralise the alkali. And it goes through pH 7. So that's pH 7, and it drops right down past it. At this point, I could read off my graph that I've added 25 centimetres cubed of acid. I must have neutralised my alkali at that point. If I continue adding acid, what's going to happen is the pH will continue to fall, but eventually it will level out till the concentration of acid is so high I've got what's called excess, which means I've added more than is necessary and the pH can't change any further. That's called a titration, and this is a titration curve. Strong and weak acids, a little bit about those. There's only sort of one tip I'm really going to give you on each. Strong acids, what we say about strong acids, such as hydrochloric acid, is they fully dissociate in water. Which means if you add hydrochloric acid to water, it will completely split up into H plus and Cl minus, the other side to it. Remember, it's the H plus that makes it acidic. The example I will give you is again, using a pen, simple example. If I had 1,000 pens and they were a strong acid, as soon as I put them in water, 1,000 of them would break off into the lids and the pen, H plus, Cl minus. Okay? All of them would do that. If I had 1,000 pens, 1,000 would break apart. That's called dissociation. They would break apart. Whereas if I've got a weak acid, what's called a weak acid, they only partially dissociate. So this arrow you see here, you might recognise as being reversible. It means this will come apart, but these will also join back together to make this. Partially dissociates means if I had 1,000 pens again of a weak acid, maybe 10 of them the lids would come off. But the other 990 would still stay with their lids on, because they're only a weak acid. They only partially dissociate. The amount of H plus, the concentration of H plus, is much lower for a weak acid, which means their pH, although still acidic, would be a higher number, something like 6, than for a strong acid, which fully dissociates, and it would be a much lower number, because you've got a high concentration of H plus, the pH would be 1, or somewhere around there. Just some terms to be aware of with acids. You get concentrated and dilute. You can take a strong acid and you can make it concentrated, or you can make it dilute. You can take a weak acid and you can make it concentrated or dilute. It doesn't necessarily mean that one would be stronger than the other. It's just the amount of water you've mixed with it. Concentrated means there's a lot of the acid with a little bit of water, whereas dilute means a little bit of acid with lots of water. So concentrated versus dilute is not the same as strong and weak. If a question's asking you about a strong acid, it fully dissociates, or a weak acid partially dissociates. Okay. So making salts. Okay, there are 3 ways you need to know to make salts. The 3 ways can be, you can add a metal to an acid and you make a salt and hydrogen. Hydrogen gas is given off. Acid plus base, or an alkali, because bases are alkalis that are not dissolved, you make a salt and you make water. This is a neutralisation reaction. And last of all, you can add an acid to a carbonate and you make a salt, water and carbon dioxide from the carbonate. This is also a neutralisation reaction. Carbonates are also basic and will neutralise acids, but they give off carbon dioxide. The salt you actually make will come from 2 things. The name of the metal gives you the first bit of the name, so it might be magnesium sulfate or copper sulfate, and the name of the metal will come from over here. It will either be the metal itself, or the base, or the carbonate will have a metal in front of it. Sodium carbonate or sodium hydroxide. Sodium is the metal. But for the other part of the name of the salt, it depends on what acid you are making. So if you want to make a chloride, you add hydrochloric acid. Okay? I'm not going to write out the acid bit each time, but hydrochloric acid makes a salt called a chloride. If I want to make a nitrate, I add nitric acid. And these are the three you need to recognise. That will make a nitrate salt. And if I want to make a sulfate, doesn't matter about the spelling, PH or F. Sorry, I've put sulfate over there. I'm just going to start that again because really I've done the acids over here. So I want to put sulfuric makes a sulfate. Okay. So that's the second bit of the name of my salt. So if I used magnesium and hydrochloric acid, I'd make magnesium chloride. If I use sodium hydroxide and nitric acid, I'd make sodium nitrate. If I used copper carbonate and sulfuric acid, I'd make copper sulfate. Okay? And a practical they do talk about is making a salt. Now, you might not have to make copper sulfate, but it's the same principles. Copper sulfate is a classic one though. You could do that by mixing copper oxide, which is a base, with sulfuric acid. The copper comes from the copper oxide and the sulfate comes from the sulfuric acid. You add excess copper oxide to the mixture to make sure all the sulfuric acid is reacted, because the sulfuric acid is harmful, so you want to use it all up, and the way you do that is you add excess, which means too much, more than's needed of the copper oxide. You heat it up to get the reaction to happen, and what you'll be left with is you'll be left with a solution which has got the copper oxide, which is a black solid, floating around in it. So to remove that excess copper oxide, you filter it through a filter paper and collect the liquid at the bottom. That liquid, if you remember seeing it, is a nice bright blue liquid. Now we don't want the blue liquid, we want the copper sulfate that's in the liquid. And the way we do that is we do crystallization. We pour the liquid into an evaporator basin and we heat it up till crystals start to form. Then we leave it for a period of time for crystals to form slowly, and we get nice big crystals formed at the end of it. Okay? That's a way to make it. If we wanted to purify those crystals, we could redissolve them, recrystallize them, crystallize them out again. We could dissolve them in something, sorry, not dissolve them, wash them with a solvent that they don't dissolve in and filter off the things that didn't dissolve. Extracting metals. You need to know how to extract metals from their ore, and you need to know the reactivity series. It used to be given, but it's not given anymore. I just generally remember it as groups of metals together. So things like potassium, sodium, calcium, magnesium, aluminium, they're quite reactive up the top. Things like zinc, iron, tin and lead, they're sort of in the middle bit of reactivity. And then copper, silver, gold, platinum, they're unreactive metals. They don't react very easily. You can always displace a less reactive metal with a more reactive metal. That means if you've got a compound with iron in it, you can push the iron out of the compound by using magnesium or calcium or sodium or potassium, any of those. Similarly, carbon appears on here because if you want to remove iron from iron oxide, carbon is higher in the reactivity series, so you can add carbon to it and it will displace it to give you iron metal, and carbon dioxide will be produced. Okay. The iron you get from this can then be made into steel by mixing a bit of carbon with it and making an alloy. Okay. So it's displacement, how you extract out metals. The ones down the bottom don't tend to need to be extracted. They're obtained in the earth in their pure form, whereas the ones at the top, higher up, they have to be extracted through the process of electrolysis, which I'm going to talk about now. So with electrolysis, don't panic. And that's a little acronym to remember. The positive electrode, which I'll talk about what the electrodes are, it's called the anode, positive anode. Negative is the cathode. Negative is the cathode. Okay? Electrolysis literally means the splitting of something using electricity. Okay? What you do is you put a solution, maybe, or a molten ionic compound, it's only done on ionic compounds, into a beaker. And that's called the electrolyte. Or if we're doing it on a large scale, it'd be in some sort of reaction vessel. you have the two electrodes. They're usually made of graphite. Graphite is good because generally it's resistant to heat, doesn't melt. It's unreactive in the main, doesn't really react with too much. And it's also able to conduct electricity. Electrolysis is all about electricity, so we need something that conducts electricity. Okay? We've got our electrodes, the positive anode and the negative cathode. The ions that are in solution are attracted to it. So positive ions, which are usually metal, are attracted to the negative electrode. They're attracted to the cathode. And negative ions, which are the non-metal in your ionic compound, are attracted to the positive electrode. In case of this, the anode. Okay? This can only be carried out if the substance itself, the electrolyte, the ionic compound, the salt, is molten, you've melted it, or you've dissolved it in water. Why can't it be done on a solid? Solid ionic compounds don't conduct electricity, as we saw earlier. One particular one they can talk about, and one is high in the reactivity series, is the purification and extraction of aluminium. I'm not going to go into too much detail, but the reaction vessel looks like this. It has a negative electrode, which is made of graphite, around the outside of the container, which is the cathode. And then it has the positive anodes as two sort of graphite rods that you dip into the mixture. The mixture itself is aluminium ore, which is actually aluminium oxide, which has been mined from the ground. They've dug it out the ground. And they mix it with a substance called cryolite. Because, as I said, ionic compounds have a really high melting and boiling point. So to make it easier to melt, they add cryolite, which lowers the melting point. I put boiling point there, but it lowers both the boiling point and the melting point. When you turn on the electrical supply, the aluminium is attracted to the negative electrode and sinks to the bottom. And then it can be run out of a little tube alongside. So molten aluminium can be run out at the bottom of the reaction vessel. The oxygen in the aluminium oxide is attracted to the positive electrodes, the anodes. And when it's there, because it's so hot, oxygen actually reacts with the graphite electrodes to release carbon dioxide. So those electrodes have to be replaced every so often because they burn away in the reaction. But that's one specific example they can ask you about, how you extract aluminium from aluminium oxide using electrolysis. In your electrolysis reactions, there's a process called redox going on. Redox literally stands for reduction and oxidation. Now, questions about reduction and oxidation are always talking about electrons. Okay? Oxidation is loss of electrons, and reduction is gain of electrons. I'll explain exactly what that means in a second, but just an exam tip is if ever a question asks you, how can you tell this substance has been oxidised? You just have to say it's lost electrons. How can you tell this substance has been reduced? It's gained electrons. Similarly, they might say this substance has gained electrons. What's happened? It's been reduced. A way you can remember that is oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Oil rig. Okay, a way to remember oxidation is loss, reduction is gain. And this would be what's going on in electrolysis. So I said the positive ions would be attracted to the negative electrode, the cathode, and this in this case is copper, copper 2+. If we did this electrolysis on copper chloride, this is what would happen. The copper would go to the cathode, and when it was there, it would pick up 2 electrons. Electrons are electricity is the movement of electrons. So they flow into the electrode, and the copper ions that are in solution pick it up, and they form copper metal. So you'd actually see copper metal, a reddish-orange metal, forming on the outside of the electrode. Similarly, chlorine is negatively charged, so it would go to the anode, the positive anode, and when it was there, it would lose electrons. Now, the way you show that is you put, goes across to lose electrons on the right-hand side. The reason it's 2 is because chlorine ions, Cl-, have to form chlorine gas, which is Cl2. And to do that, you need 2 chloride ions, I should say, and they give out 2 electrons. And the electrons actually balance, and that's good because this is the 2 reactions that are happening. At the anode, electrons are being generated, they're passed through the wires and come down to the cathode where the copper picks them up. Here you would see chlorine gas being produced. Now, just going back to one thing with electrolysis, if you do it on solutions, if your metal is really reactive, the metal itself won't form at the negative cathode. If it's higher in the reactivity series than hydrogen, you will get hydrogen gas released, because as soon as it's produced, it will react with water if it's in solution. If it's molten, if it's just a liquid metal ionic compound, it will form the metal, such as in the example of, and I'm jumping around a little bit, aluminium oxide. That's molten aluminium oxide, so the aluminium will form in this case. But if you've dissolved your sodium chloride, say, in water, then sodium will react with the water and release hydrogen gas. Hydrogen gas is produced instead of sodium. Similarly, and this is just a tip that you'll just have to remember, one that occasionally comes up, if you're doing electrolysis on a copper sulfate solution or any sulfate solution, instead of sulfate or sulfur being formed at the positive anode, you get oxygen gas given off. Sulfate does not form, oxygen gives off. But again, that's if you're doing electrolysis on solutions. Right, little time left. We have one topic left to cover, so let's get through this and we'll be done. Okay. Energy changes, exo and endothermic. You should have come across these words. Exothermic reactions, they give out energy. Exothermic, exit. Energy exits, it's given out. That's where the word is sort of derived from. Because it's giving out energy, think about you. If you're giving out energy, or you're getting hot and you're giving out heat, you cause the temperature around you to go up. The temperature rises. So exothermic reactions get hotter. They give out energy and they cause temperature to rise up. Okay? An example would be burning something. If you burn a piece of wood, it's an exothermic reaction. It gives out energy. It gets hot. Some of the examples of uses, now they used to talk a lot about this, it might not be as much relevant in the new spec, but they do like application of knowledge, is a self-heating can. So they used to have these cans where they had a little button on the bottom, you pressed that, it mixed two chemicals, it was exothermic, it gave out heat and it got hotter. Or hand warmers, you get those little packets you can break, put into your gloves and it warms up your hands on a cold day. That's again, contains two chemicals which when they react, it's an exothermic reaction and it gives out heat. The opposite to exothermic is endothermic. Endothermic reactions take in heat energy. Okay? They cause the temperature to go down and get colder. An example would be photosynthesis. Now that's a bit different because it takes in light rather than heat energy, but it is an example of an endothermic reaction. Also, an example, and a good use, is in those cold packs that you might get from the nurse. You actually have to snap them, the chemicals mix inside, they take in heat energy from their surroundings and they cool down. Now, I'll go back to the slide I jumped through. I thought this was actually better to go to next. This is what we call a reaction profile or an energy level diagram. It actually shows it for an exothermic and an endothermic reaction. And a few things to point out are relevant. This is the line for the reactants. This is a measure of the energy in the reaction. The reactants in an exothermic reaction are found here. And the products are lower down. That's because this energy, this drop here, this fall from reactants to products, is equal to the energy that's been released or given out. And that's the energy that warms up the temperature around it. So the overall drop is down for an exothermic reaction. But even though the overall drop is down, there is still a hump to get over, which is called the activation energy. That's the energy you need to supply for the reaction to start. If I was to turn on this gas tap right now, gas would come out and methane would be released. But the methane wouldn't just catch fire, it has to be supplied with a spark or a flame initially to supply the activation energy for the reaction to start, and then it would start giving out heat, it would get hot, it would give out energy. When it gives out its own energy, it releases enough energy to keep going, to activate the rest. But the diagrams are quite important. They sometimes ask you to label up these different sections, the energy released and the activation energy. Reactants higher than products, means it's an exothermic reaction, energy is released. For an endothermic reaction, it looks very similar, but instead of going down, the reactants are lower than the products. There's still a hump to get over, it still has to go up this hill, and then it falls, but it doesn't fall as far, and energy is actually absorbed or taken in as the line goes up. The activation energy for this reaction is quite large, because there's a big amount of energy to overcome, to supply for the reaction to start. And often, if you stop supplying the energy in to an endothermic reaction, the reaction will stop. It can't keep itself going because it just needs to absorb more all the time. It doesn't release any to keep itself going. Okay. They're called energy level diagrams or reaction profiles, and therefore exo and endothermic reactions. That's what they look like. Last two bits then. We are very close to the end. Might run over a little bit. Hope you'll stay with me. I hope I'm allowed to go on a bit. There is an investigation, a practical that you may have to do to investigate temperature change. Very simply, you might do a reaction inside a polystyrene cup. So you take a polystyrene cup, you put a thermometer in it, and you record the temperature before you've added a second reactant to the beaker or the cup. So I've put a solution in here, I've measured the temperature. That's called the initial temperature. I then add a second chemical which is going to react with it into the beaker. A reaction starts to happen and I might see the temperature go up or I might see the temperature go down depending on if it's exo or endothermic. I then record the final temperature. That means when the temperature stops changing, I take the temperature at the end of the reaction, when it's stopped going up or stopped going down. Okay? I can then see the temperature change that I have got and I can tell whether the reaction is exo or endothermic. Has the temperature increased or decreased? If I want to do an investigation in this, what I could alter is I could change some different things. The variable that I change is called the independent variable. And the independent variable in this investigation would be the concentration of the solution, maybe, that I put into here. I could try different concentrations and see if that made a difference to the temperature change. I could try different types of reactants. Do I want to add a metal and an acid, or an acid and a base, or an acid and a carbonate, as I said in the reactions to make salts earlier? I could try those. Or I could try a displacement reaction between chlorine and potassium bromide, as I talked about when I was talking about halogens. I could alter the size of the reactants. Do I want to put in a big lump of reactants, or do I want to break it up into small pieces and crumble it in, thereby increasing the surface area? Is another thing I could change. These are all variables I could investigate. The dependent variable, what I've been measuring, would be the temperature change. Okay, that's the temperature change is what I'm actually measuring in this investigation. Has it gone up? Has it gone down? What is the difference? If I change the concentrations, does it give me a big rise in temperature for a concentrated solution and a little rise in temperature for a dilute solution? Okay. Control variables would be things I would keep the same in the investigation. So I would want to keep the overall volume of liquid the same. I might want to keep the masses of some of the reactants the same, depending on what I was altering. The biggest problem with this experiment, just doing it in a cup, is generally heat loss to the surroundings. In this one, it's a very crude setup. The first thing I could do to make it better is I could just put a lid on it. Okay, that would trap some of the heat in here, and it would mean that I wouldn't lose heat to the surroundings. But also I could insulate the cup further, or I could make sure there's no loss of materials. When looking for things you can control, or how you can improve the experiment, you can't just put things like measure it better, or human error. You have to say exactly what is going to improve. In this one, first thing I do would be put a lid on it. That's how I would improve that experiment. Okay. So the very, very last thing, and we've gone a little bit over now, I'll just draw it to a close, is bond energy calculations. In every reaction that happens, some bonds are broken and some bonds form together. Okay? The breaking of bonds, like this, so if I've got a bond, I have to supply energy in to break it apart. That takes energy supplied in to actually break a bond. Whereas when I make a bond, it actually gives out energy. If I do that, my fingers rub past each other and they get warm because of the friction. That's giving out energy. So breaking a bond takes energy to pull it apart. making a bond actually gives out energy. You could be asked to do some calculations on that. You might be given a reaction like this, and also what you should be given in the question is some reactants drawn out like this. You'll also be given some values for each of the bonds that are involved. Now what you need to do is identify the bonds that are formed, and I'm just going to do this on the board as the very last thing, is I look at what bonds are there. In this case I've got carbon joined to a hydrogen. So I've got carbon joined to a hydrogen. I'll just draw it out exactly like that there. Then I look how many I've got. I've got 1, 2, 3, 4 of those bonds. So I've got 4 of them. Okay. Then I've got oxygen with another oxygen, and that equal sign actually means it's a double bond between them. And how many do I have? I have 2 of them. So times by 2. These are my bonds being broken. Okay, so that's my bonds being broken. That's it. Then I've got my bonds being made. My bonds being made are the other side, or formed it might call them, but bonds made. The numbers that you'll be given will be the same whether you are breaking them or making them. Okay, in this I can see I've got a C double bond to an O, and I've got 2 of those in there. So times by 2. I've got, if I step out of the way, oxygen with a hydrogen, so O to H, and I've got 1, 2, 3, 4. If I've drawn it out, or I've got it drawn, and I put a line through each when I'm doing this, I know I've got them all. So I know I've got all my bonds. We're sort of part of the way there now. This is where I'm not going to take any further, but I would need the numbers. If I had the numbers for the energy of this bond, I would just take the number from the table I was given, times it by 4, and get a value. Similarly, I'd have the number for this bond, and I'd have to times it by 2, and that's the energy I would have for the bonds being broken. When bonds are broken, last tip is bonds broken gives me a plus sign. So whatever these 2 numbers are, I add them together and I put a big plus in front of them. For the bonds being made, when I make a bond, I make a minus sign. Okay? That means I'm going to do this value, times it by 2, do this value, times it by 4, put those 2 together, and then stick a big minus sign in front of it. The last thing I need to do in this calculation to work out the overall energy change for that reaction is I would just do this, type it into my calculator as a plus, minus whatever this number had come to when I've worked out those bonds. They're called bond energy calculations. Again, a little bit of maths, a little bit tricky, can be worth up to 3 or 4 marks, but if you follow the process, you'll certainly get some of the marks, and you could potentially get all of them. Okay. Thanks for watching. We are at the end. Oh,
Miss Walker says she will be available on email for the next 30 minutes.
Okay, again, so on that contact science at folkestoneacademy.com, Miss Walker will still respond to your emails, and as I say, I'll be in the morning. We'll say officially from 8 o'clock because that was the time it's given, but I'll probably be in a bit before that as well to go through any bits. If you want to go through any of these bond energy calculations, balancing equations, reactive mass that I didn't talk about, or anything that's come up from your own revision, do bring it in. Other than that, good luck for tomorrow, and I'll see you there.